We can also use implicit differentiation to find the derivative of the arcsecant. Suppose y is equal to the arcsecant of some number x. Then we know that y is an angle between 0 and pi, and that the secant of y is x. Of course, the secant is 1 over cosine, so if the secant of y is x, then the cosine of y is the reciprocal of that, 1 over x. Let's use implicit differentiation. We'll take the derivative of both sides with respect to x. Now 1 over x is x to the negative 1, so the derivative of this side is going to be negative x to the negative 2, or that's negative 1 over x squared. On the other side, the derivative of the cosine is the negative sine, and then we multiply by the derivative of that inside function. Since y is a function of x inside cosine, the chain rule says you take the derivative of the outside, evaluate the inside, times the derivative of the inside. Now we can solve for dy dx. We find that dy dx is, since there's a negative here on both sides we can multiply through, we find that dy dx is 1 over x squared times the sine of y. Now, we actually know that since cosine squared y plus sine squared y is equal to 1, we know that the sine squared of y is 1 minus the cosine squared, and that would mean that the sine of y is either plus or minus the square root of 1 minus cosine squared y. In fact, we know that because y is an angle between 0 and pi, the sine of y has got to be positive, right? No matter where it is, you've got a positive value for the sine. So we know that the sine of y actually has to be positive square root of 1 minus cosine squared y. And we know that the cosine of y is 1 over x, so the sine of y would be the square root of 1 minus 1 over x squared would be 1 over x squared. So now we know that dy dx is equal to 1 over x squared times the square root of 1 minus 1 over x squared. It's nice, but we'd like to simplify. It's bad to have a fraction underneath a square root, so if I can avoid it, what I'll do is I'll get rid of that fraction. What I want, I'm going to multiply this top and bottom by x squared so I get a common denominator. Now I have x squared over x squared minus 1 over x squared. That would be x squared minus 1 all over x squared. But the root of the quotient is the quotient of the root, so I can write this as x squared times the square root of x squared minus 1 all over the square root of x squared. Now, x squared is the same thing as the absolute value of x squared, right? The sign doesn't matter when you square a number. Then we have the square root of x squared minus 1. And the square root of x squared is also the absolute value, because if the number was negative, the negative would get squared away. When you take the square root, you get the positive version. So this is actually also the square root of x squared is the absolute value of x. Notice I have an absolute value of x squared in the top and an absolute value of x down below. So they cancel. So I have 1 over the absolute value of x times the square root of x squared minus 1. Now, we've seen that the derivative with respect to x of the arcsine is 1 over the square root of 1 minus x squared. The derivative with respect to x of the arctan was 1 over 1 plus x squared. And the derivative with respect to x of the arcsecant was 1 over the absolute value of x times the square root of x squared minus 1. See if you can use the same technique of implicit differentiation to show these, that the derivative of the arc cosine of x is negative 1 over the square root of 1 minus x squared. The derivative with respect to x of the arc cotangent is negative 1 over 1 plus x squared. And the derivative with respect to x of the cosecant inverse of x is negative 1 over the absolute value of x times the square root of x squared minus 1.